Oh, okay. Welcome to lecture for day 10, I guess. Today we're beginning chapter 7. That means that we're a little bit ahead of schedule, quite a bit ahead of schedule, actually. And I want to keep going, mostly because, according to the schedule, next week we're supposed to cover 3 chapters in 1 week. And that's going to be pretty challenging, although it should be quite feasible as long as we keep going when we're ahead like this. So in order to avoid getting behind schedule, I'm going to keep going with being ahead of schedule. Don't worry though, I am continuing to assign the homework due dates according to the schedule. So as far as the homework due dates are concerned, we're not ahead of schedule, we're right on schedule. But I'm going to keep going just so we don't get behind. For this chapter, we get into the quantum mechanical model of the atom. This is where stuff gets fun. This is sort of the heavy physics section of chemistry. And we'll try to keep the actual physics to a minimum. But this is the section of chemistry that was actually developed the most recently. And it's the type that involves, if you want to go into it in detail anyway, some pretty heavy duty physics. To begin with, the first section, section 7.1, is quantum mechanics. Okay, so quantum mechanics deals with very small stuff. This is necessary because the previous models for how things behave, particularly with regard to movement, were devised by Isaac Newton around 1700. That was a long time ago, and Newton was actually remarkably correct in his theories of how objects behave when they're in motion. But it turns out that those theories only really apply to larger objects. By larger, we mean basically everything down to the level of atoms. Once you get to the level of atoms and things smaller than atoms, like protons and neutrons and electrons, you're kind of in a whole different world where Newtonian mechanics don't really apply anymore, and we need alternative models for how things behave. That alternative model for how things behave turned out to be quantum mechanics, as opposed to Newtonian mechanics. Quantum mechanics was they were first really started developing quantum mechanics, I guess, back around the teens of the 20th century. And it took several decades for it to really come to fruition. And that's the model that we use today for explaining how subatomic particles behave. So in chemistry, when you talk about small stuff, we're basically talking about atoms and subatomic particles. And so those are extremely small by everyday standards. And so people in Newton's time didn't even really think on size scales like that. Okay, so the subatomic particles are actually responsible for many of the chemical and physical properties of various substances. Basically, as we were talking at the very beginning of the semester when we were talking about the debates about whether atoms exist or not back in ancient Greece. Well, of course, we know now that atoms do exist, and the reason that substances are the way they are is basically based on the properties of their atoms. And atoms are the way they are because of the properties, or the numbers, rather, of the subatomic particles that make them up and their behavior. And so for that reason, we have to really come to understand the subatomic particles and why they behave the way they do. It turns out that even with quantum mechanics, positions of subatomic particles, especially electrons, are very difficult to understand. That's especially true for electrons because electrons are so much smaller than protons and neutrons. That makes their behavior so much more unusual by everyday standards, as opposed to protons and neutrons. The reason that these can be so difficult to determine is that we normally rely on visible light bouncing off an object. In fact, visible light bouncing off objects is how we locate most things. It's how you locate the doorknob when you want to go in or out of a room. It's how you locate your keys when you pick them up. It's how you locate another person when you go to, say, kiss them or slap them, as the case may be. We rely for all of that on our vision, which is based on visible light bouncing off objects and entering our eyes. The problem is that that's really hard to do with small objects small objects on the scale of subatomic particles, because for one thing, they're really small. So finding them even with, even if you have light bouncing off them can be difficult, but also because the size of the particles is so small that light bouncing off them can actually change their position. Just the amount of force of a photon bouncing off an electron can actually cause the electron to move. And so observing something actually changes what you're observing. Actually, the same is true of everyday objects, but to a much smaller extent. If you, say, look for a pen that's lying there on the table, just the fact that visible light is bouncing off that pen changes its position a little bit, as opposed to where it would be if there were no light at all bouncing off it. But for an object the size of a pen, that change in its position is so minute that it makes no difference in practical terms, and we can go and pick up the pen just fine. With something as tiny as an electron, though, photons bouncing off that electron can change its position significantly compared to where it would be without the light bouncing off it. And that makes it very difficult to observe things on such a small level. And because of that, because things like electrons behave differently when they're observed versus when they're not observed, it can be very difficult to understand the behavior of objects like that. So you could say that because of that, our knowledge of electron behavior is actually quite limited. Quantum mechanics was developed in order to explain the behavior of matter at the smallest level. And so basically you needed a whole new theory to understand how matter behaves at the very smallest levels. Okay, so our goal was to explain why matter behaves the way it does. Related to this is the behavior of light. It's really intertwined with the behavior of matter at the smallest levels. And so this would be a good time to look into the nature of light. Actually, light has a lot of things in common with electrons. And so, like I said, this is a very good place to kind of look at the behavior of light. For one thing, light and electrons both have what's known as wave-particle duality. Wave-particle duality means that they have basically some properties of waves and some properties of particles. Actually, it turns out that everything has wave-particle duality to some extent. Everything has some properties of waves and some properties of particles. A person walking down the street trails an energy wave after them. It's just that basically the bigger the object is, the less significant the wave properties are. So it's when you get down to the tiniest levels of matter, that's when the particle properties and the wave properties are both significant at the same time. Okay, so we'll look at the wave nature of light. Light is a form of electromagnetic radiation. And electromagnetic radiation is a type of energy that travels in waves. Waves are basically, in this case, it takes the form of oscillating electrical and magnetic fields. And by oscillating, we just mean that they go up and down periodically in time. Sort of like, waves in an ocean do. The magnetic field is a region where magnetic particles experience a force. And an electrical field is just, in general, a region where electrically charged particles experience a force. Okay, and electricity and magnetism are very definitely related to each other. An example of an electric field is just, if you think of a proton has an electric field around it because it has an electric charge. If any other charged particle approaches it, it experiences a force. If the particle approaching is positively charged, like the proton is, then it will experience a repulsive force. And if the particle approaching is negatively charged, unlike the proton, then it will experience an attractive force toward the proton. And as it turns out, waves of electromagnetic radiation, which is kind of tedious to have to write over and over again. So I'll say, I'm going to use an abbreviation from time to time, EMR for electromagnetic radiation. Waves of electromagnetic radiation, anyway, are made up of, or consist of, perpendicular electric and magnetic fields. So if the electric field is oscillating up and down in the plane of the paper, the magnetic field would be oscillating in and out of the paper in step with the electric field. That is really hard to draw, especially for somebody with limited artistic skills like myself. But if we look in the book at the beginning of chapter 7, we can see what they're talking about. Okay, so chapter 7, the first figure in chapter 7 gives you a better idea of what we're talking about here than I can possibly draw. You notice how one of the fields, the electric field, goes up and down flat against the paper, while the magnetic field is coming in and out of the paper at the same time. And the peaks and valleys of the electrical fields and the magnetic fields line up with each other. It's just that they are perpendicular to each other. Okay, so that's what we're talking about here. Electromagnetic waves of all kinds travel forward through space at the speed of light. And that equals 3 times 10 to the 8th meters per second in vacuum or air. So this is a well-known number. You can look it up. It's in all the standard tables for for constants in chemistry and physics. The speed of light is also symbolized by a lowercase letter c. And in non-SI units, in fact, non-metric units, it's 186,000 miles per second. And that would be the speed of light in vacuum or in air. Actually, the medium through which the light is traveling has an effect on the speed of light. We often think of the speed of light as being a constant, but it's a constant in air or in vacuum. The speed of light, say, in water would be significantly slower than 3 times 10 to the 8th meters per second. And the speed of light in glass is significantly slower than 3 times 10 to the 8th meters per second. It's 3 times 10 to the 8th meters per second in a vacuum because in a vacuum, there's really nothing to slow it down. A vacuum is literally nothing. And in air, the particles in air are far enough apart that the speed of light is a little bit slower than it is in a vacuum, but it still rounds off to 3.00 times 10 to the 8th meters per second. So we consider that to be the speed of light in either air or vacuum. And it doesn't matter what type of electromagnetic wave you're talking about. As you may know, as we'll definitely go over in detail in the near future, in case you don't know, electromagnetic radiation takes in a wide variety of stuff. Radio waves are electromagnetic radiation. Microwaves also are. Visible light, infrared, ultraviolet, X-rays. Those are all types of electromagnetic radiation. And all of their waves travel at the speed of light. So the type of electromagnetic radiation does not affect the speed with which it travels through air or vacuum. Okay, this is much faster than what are known as mechanical waves. Mechanical waves are waves that depend on larger chunks of matter. So for instance, sound waves travel through air, so they depend on the oscillation of particles in the air, like oxygen and nitrogen and carbon dioxide and things like that. And sound travels, at 340 meters per second, which, as you notice, is quite a bit less than 3 times 10 to the 8th meters per second. And that's what's responsible for the delay between seeing something and hearing something when it happens at a distance. The delay between, say, lightning and thunder is a manifestation of the difference between the speed of light and the speed of sound. When lightning strikes, the flash of light travels from the bolt of lightning to your eye at 3 times 10 to the 8th meters per second. That flash of lightning is super hot, and what it does is it superheats the gases around it, you know, the air, the oxygen and nitrogen and stuff like that that make up the air. And when gases heat up, they expand hugely. So the big increase in the temperature of the air around the lightning bolt will expand the air in that vicinity to a huge extent, and those particles in the air will bump against other particles that are a little further out, and those particles will bump against other particles a little further out, and so on and so on and so on, until those particles that are, you know, get bumped eventually reach your eardrum and shake it back and forth, and that is what we perceive as thunder. That process, though, takes a lot longer than it takes the light to get to your ear, because those the sound waves are only traveling at 340 meters per second. And so that's why you can actually calculate how far away the lightning was by how long it takes the thunder to reach your ear after you see the lightning strike. And it's something like 5 seconds per mile. You know, so if it takes 10 seconds for you to hear the thunder, that means the lightning was 2 miles away. Okay, so waves are characterized in several ways. One of the things that can characterize a wave is amplitude. Amplitude is just the height of the peak of the waves above the midline. The peaks of the waves are also known as crests. or the depth of the troughs between waves below the midline. And so if you have, say, a midline of a wave and you have a wave that goes like this, that's a pretty badly drawn wave, but you get the idea. That height right there would be the amplitude. Or this depth right here would also be the amplitude. And the midline would be the line, your horizontal line that sort of goes right down the middle of the waves. And it's the amplitude that determines things like brightness if you're talking about visible light, or loudness if you're talking about sound waves. Okay, also another way of distinguishing waves or characterizing waves is wavelength. Wavelength is the symbol of the Greek letter lambda. This is a lowercase lambda, which is the Greek equivalent of L, because we've already used L in chemistry and physics for other things. So, capital L means liters and lowercase l usually means length. And this is a form of length, but it's a special kind of length. So they decided to use a different version of L rather than just using L. And this is the distance from crest to crest, or trough to trough, for a given wave. And this distance differs for different types of electromagnetic radiation. Remember, ERM means electromagnetic radiation. Or sorry, that's EMR for electromagnetic radiation. Maybe I should just write it out. So wavelength is short for high energy electromagnetic radiation. And so that would be, so for instance, X-rays. And wavelength would be long for lower energies. And so that would be, for instance, radio waves. The wavelengths for something like X-rays would probably be on the order of maybe 10 to the minus 15 meters. So they are really, really short waves. On the other hand, radio waves or television signal waves can be on the order of even kilometers in length, from the peak of one wave to the peak of the next. So there is actually a huge difference in wavelengths, and there's a huge difference in energies for electromagnetic radiation, depending on where it is along the spectrum. The SI units for wavelength would be meters. And we don't always actually use meters for measuring wavelength because of the different vastly different sizes of waves. So sometimes we might use meters, sometimes we might use smaller units like nanometers or something like that, because we want generally to have a relatively convenient number to deal with. Okay, I'm going to stop there for the moment because this is about 30 minutes, and we'll pick up with part B in just a moment.